This is further stats 1 from 2022. First question, we've made some observations about 100 liters. You've got these numbers here. You've got an expected row down here being formed by this binomial here. So to find the expected number for 1, we just say what's the probability of being 1 based on this binomial. So binomial PD function in the calculator will get this, it's that. Of course, we're doing 100 observations, so times that by 100 to find the expected value, which is of course 25. And then you can work out S just by doing 100, take away this, take away this, take away 25, take away 25. Or you could just find one probability of x equals 2, that times by 100. Either way is fine. You get this, carry out a suitable test. So firstly, null hypothesis is that we can model this suitably with B4, 0.5. H1 is going to be that we can't. So that's fine. We've got to work out x squared now. This thing here, I like using this formula, this squared over this, plus this squared over this, plus this squared over this, and so on. Gets me all this. Take away the n, 100, right at the very end, you get this number here. Now, our degrees of freedom, we have 1, 2, 3, 4, 5 columns. All of them are bigger than, all the expected values are bigger than 5, so we don't have to get rid of any of them. So there's 5 columns. The only restriction is that they need to add up to 100. So we've got 4 degrees of freedom here. And then get out the chi-square table. V is 4. This box here is 0.05, 5%. Find this number. Our test value is bigger than that. And so we're in the critical region, therefore, and we reject H0 and say the model is not suitable. Question 2 then, E of x is just this times this, plus this times this, plus this times this, and so on. That's very straightforward. These are all numbers, so we just end up with that. Variance of x. Now, the formula for variance is E of x squared minus E of x all squared. Now, this we can work out because it's just this squared times this, plus this squared times this, plus this squared times this, and so on. And remember, when these squares, they become positive, so that's going to be quite relevant. And then E of x is just this. If that's all being squared, that's 0.2 minus 1, all squares there. So we get 0.04b minus 0.2b minus another 0.2b plus 1. And we'll attach that on the end. This is all just numbers here. Variance we already know, so I've just filled in everything I know into this formula here. We get this, we simplify, we throw that in a calculator, and we get b is 11. There's also a negative value that I couldn't even bother to write down because it tells you b is positive. Sorry, it tells you b is greater than 5. I can't even remember. Maybe the other value was like between 0 and 5. I don't remember, but this is the only one you can have. And yeah, find the probability of this here. So this is a little bit more complicated, but essentially for any x that you have here, let's work out 2x minus 3x. So for this x here, maybe, I've got 11 as b, by the way. For 2 minus 3x, if x is minus 5, that makes 17, I think. And if x is minus 1, that makes 5, and so on, and so on, and so on. We'll just do that every time. And we'll do the same thing with x squared. Now, of course, this squared is this. We've actually already done this. It's down here. And what we can say is, okay, so for which x values is x squared less than 2 minus 3x? So this one, x squared, is bigger, so that doesn't work. This one, this is less than this, so this is a good one. Minus 1 is a good one. 0 also does it. This is less than that. And then the other two don't. Right? So the only two values we can be is minus 1 or 0. Those are the only two values of x that actually do this. And therefore, the probability of doing that is 0.25 plus 0.1, just because those are the probabilities of being those two things. And we just combine them, and we get the answer of 0.35. Question 3 then, so this is about the Poisson distribution, I guess. Daily rate of 0.4. This time, but we're modeling for 28 days. So we'll do 0.4 times 28 and do a Poisson distribution for 11.2. And we'll find the probability of greater than or equal to 19, which is, of course, 1 less than the probability of less than or equal to 18. Type this into a calculator, Poisson cumulative function, we get this, which will turn out to be that. Randomly selects 250 days from the last 3 years. Using Poisson approximation, estimate the probability of at least 20 of these having more than one call. Okay, so firstly, what we'll do is we'll say x, I'll explain that in a second, is Poisson with 0.4. So let's find the probability of just getting more than one call in any given day. So in one day, we get 0.4 per day on average. So the probability of getting more than one call is this, which is 1 minus the probability of less than or equal to 1. We can, of course, just do Poisson PD cumulative function, sorry, here, and we get this, which is that. So that's the probability of getting more than one call per day. And now what we're going to be asking is, if we set up 250 days, each with this probability of more than one calls, well, that's a binomial distribution, right? Days is 250, probability is this. But it's not telling us to use this binomial distribution. It's telling us to actually approximate with a Poisson. So to approximate with this Poisson, you times these two things together to get your new lambda, and then you just say, okay, what's the probability of at least 20, so that's greater or equal to 20, with this Poisson approximation here. And that's, of course, 1 minus less than or equal to 19. Put in the Poisson cumulative function, and you get this as your answer, which is there. Just to explain these letters here, the examiner's report was very specific that it said it would start marking people down if they didn't use different letters when they get out different distributions. And I used X twice here, and I was so lazy that I just put a dash after it to fix it. Anyway, so maybe just be a bit careful of that. Mountain Rescue Team A believes the number of calls per day is lower in the winter. So let's test this then. We'll say H0 is that lambda for 42 days. 42 times 0.4 is this, I believe. So we'll say H0 is just lambda would be that, and H1 is lambda is less than that because we're testing whether it's decreased, whether it's lower. So okay, what's the probability? So we'll just say some distribution Poisson with 16.8. What's the probability of having less than a root to 8 calls? Well, it's that, just using my calculator again, which is lower than 0.05. So at the 5% significance level, this is within the critical region and we'll reject H0, so that's fine. Again, throw in as much context as you want to. I've said this before in these exams, so just say something like that at the end, just to make sure you definitely don't miss something in the mark scheme. Okay, during the summer, there's a different mountain rescue team that has a different rate of calls, about half as many. C is the total number of calls received by both teams. Now, if the things are independent, which it says that they are, you can just add up those two rates to get a new rate and a new Poisson distribution. So we can just say the rate of calls for both of them together is 0.6 per day. Now, I don't know how many days there are, so I'm just putting 0.6n. So for example, if there were 10 days, this would be Poisson with lambda of 6. Like I'm just multiplying up like I did to get this and like I did earlier, but I don't know what n is, so I'll just leave it like this for now. Given the probability, find the probability then essentially for the minimum value of n, such that the probability of getting 0 calls in this combined distribution is less than this. Now, this is kind of an unusual question. For the first time, I think in FS1 history, we actually have to break out the Poisson, like the formula to do the Poisson distribution without a calculator, which is this here. And this is not usually very helpful because this is a very hard equation to solve. But actually, when x is 0, it goes pretty well, because when you put in 0 to this just becomes 1 and it goes away. When you put 0 into the factorial, I mean, anything in factorial is fine, but this goes away as well, essentially. So we're just asking, we've got our lambda as 0.6n. We're just asking, when is the probability of x equals 0 less than 0.001? Of course, all this goes away, like I said. Take a log of both sides and then divide by minus 0.6, which swaps the sign, remember? And we get n is bigger than this, which means n is 12 or bigger, or the minimum value would be 12 for this. Write down an assumption. Always you can say something about independence. So the calls in each interval may be independent. So like we've assumed maybe that, imagine you were stuck on the side of a mountain and you called them and they said, oh yeah, we'll be over in a second. And then they weren't. You would probably call them again, right? Like, so those two calls weren't independent. So something like that would be an assumption that we're making. Okay, in a game, a spinner is spun repeatedly. When it's spun, the probability of landing on blue is this. Find the probability that first time it spins is on the 6th. So what that requires is it requires 5 red spins, is it? Or 5 non-blue spins, we'll just say, 5 non-blue spins. And then the 6th needs to be blue. So non-blue is 1 minus this, which is that. We need 5 of those in a row, then we need a blue, and we'll get that there. First time before the 6th spin. So this is just 1 minus the probability of getting it on the 6th or after, right? Which seems like a stupid way of doing this. Like usually we try and turn greater than equals into less than equals. But the reason this is quite nice is because the way to work out the probability of getting it on the 6th or after spin is really easy. It's just, all that requires is 5 non-blue spins in a row. Like as long as you have 5 nons and blues in a row, it doesn't matter what happens after that. So we can just do 1 minus 0.89 to the 5, and we'll get this number here. So that's cool. Exactly 4 times during the first 6 spins. So what that requires is just a binomial, isn't it? What it requires is we need 6 choose 4, and we need 4 lots of the blue, and we need 2 lots of the non-blue, and that's very straightforward. Last one, a little bit more complicated. We'll actually get out a proper distribution for this. We could have used proper distributions for these as well, but I kind of just winged them. For this one, though, 4th time before or on the 6th spin. Now, if you were asking what the probability of getting it 4 times on the 6th spin, that's a negative binomial. Now, we're saying 4 times on or before. So what we can just say is the probability of that is the probability of getting it on 4 spins plus the probability of getting it on 5 spins plus the probability of getting it on 6 spins. We can just add up those cases, right? Because you can't get it in under 4 spins, right? Because you need to do 4 spins at least. So it's just the probability of these, and it's negative binomial. So this one is just asking I mean, this one's very simple, right? We just need 4 blue spins, so that's just this. This and this, I've just filled in the negative binomial formula. So this is the property of getting your fourth on the 5th spin, and it's just this, using this formula here, using r is 4 because that's the key number we're looking for, and in this case x is 5, so I've just put 5 in there. In this case x is 6. I'll add all those results together, and I'll get this here. Next, these two people are playing a game. They take turns to spin it. Winner is first one to land on blue. Shows Zach winning. So if she's the first person to spin, for Zach to win, he requires her to miss first, which has probability of this, and then he needs to spin blue. Now that's the probability of him winning on his first go, which he doesn't have to. Next, what could happen is she could miss. She could miss. He could miss. Then she has to miss. Then he has to hit. And that's the probability of him winning on his second go. And after that, she has to miss, then he misses, then she misses, then he misses, then she misses, and then he hits. And that's the probability of him winning on the third go, on his third go, and so on. Now, this is very similar to something that was in the 2021 paper. This is just a geometric series being added. The first time is this, and the ratio between each one is you just shove in an extra 2 0.989s to represent the 2 extra misses that have to happen each time. So we just have this, and of course this thing squared is less than 1. So this is less than 1 here. So we can break out this formula from A-level maths. We'll just shove in A is this, and R is this, and we'll just get the sum, which is this, and that will be his answer, or his probability of winning overall. 5 then is the central limit theorem question. Got a geometric distribution this. So let's just break out the geometric table here. There's the stuff that might be relevant. Now from the central limit theorem, the mean of a sample is normally distributed with mu here and then sigma squared over n being the size of the sample here. Now we can work out all these things because the table tells us how to work out the mean of a geometric distribution with parameter or probability this. So 1 over p is that, which is this, and the variance we'll just shove in as well. The variance is sigma squared, is this here. So we can put both of those two things into here. N is 150, 150 times 9 is this here, and we'll be good to go. We can just work out the probability of being less than 3.45 now. Remember, when you do this in a calculator, you need to use this as your mean, and you need to use the square root of this as your standard deviation, and we'll have this result here, which will be the answer, and it's a very quick question done, as long as you just know the central limit theorem idea, which is this. So the probability generating function then, the key thing about generating functions is the probability of v equaling v is the coefficient of t to the power v. So therefore, this generating function can be written as 9 over 25 times t to the 2, plus 12 over 25 plus t to the 3, plus 4 over 25 times t to the 4, because therefore we've got the probabilities of v equaling v as the coefficients of those respective numbers here. And from here, all we have to do is turn this into this. We can vectorize out t squared, which will get us this, and then you can just wing it here. Just slam this one down. And yeah, it seems like it makes sense. This thing times this thing is that, and then this times by 2 is this, I think, and then this squared is this. That's good, it works. And then we have a different generating function, which is this one here. Use calculus to find this. This is actually in the formula book. We have the expected value of x, or some distribution function, is equal to the differential of that evaluated at 1. So we differentiate this. We're going to have to use some product rule here. Differentiate that and it goes away, and then leave this one alone. Differentiate this, the 5 comes down to make this a 5, but then you also times by the derivative of this, which is 2/5. 5 times 2/5 is just 2, and then you lower that power to a 4. You leave the t alone, and that'll be that. Sub in t is 1, and it actually turns out very nice because that turns out to be a 1, and so does this, and so does this. Yeah, it all goes quite well. You get that as 3, so that's fine. The variance then, this is also in the booklet, it's down here. So we have to differentiate again, which involves more product rule. This one differentiates, you just bring the 5 down, times by 2/5, and then lower that to a 4. It's the same thing we did before. Differentiate that, and it just goes away. Leave this alone, and then leave this alone. Differentiate this. 4 times 2 is 8, times the 2/5 you get from the bracket is 16/5, and then lower the power down. Sub in t is 1, and you get eventually this. And then we just have to do this plus this minus that squared, and we'll get our answer of this. Now, another useful result coming up here, given the two things are independent, what's the probability generating function of a new function, which is those two added? You just multiply them together. This is also in the formula book, so it's super useful. Just multiply your distribution for GW and GV in this case. So multiply these two together. Of course, the t's can go together for t cubed, and these powers here, these are all the same, right, inside the brackets, so the powers can add up, and we'll get this here. Last useful result to use here, the discrete variable is this, find the probability generating function of y then. Well, the formula here is that whatever number is in front of the x, that goes in with the t inside the function, and this number here goes outside over here. So you always do t to the power whatever this number is, and then g of the old function, and you replace t with t squared if this is a 2, or t cubed if this was a 3, or so on. So that number is there, and that one is there. And we just have to modify this now. So gy of t times this whole thing by t to the 3, and then replace all the t's with t squareds. So replace this t with a t squared, which makes it t squared cubed, which is t to the 6. Replace this t with a t squared, so nothing else changes. T to the 6 times t to the 3 is t to the 9, and we'll end up with that. Find the probability that y equals 15. So that, like we said right at this top, that's the coefficient of t to the 15. So, okay, we've got a t to the 9 here. So actually what we need is we want the coefficient of t to the 6 from here. So we could do some binomial expansion here. I'm not going to bother. I'm just going to think, well, where would t to the 6 come from here? It would come from having 3 of those and 4 of those, because of course you need to add up to 7. So 3 of those gets me to t to the 6, and then just 4 of those. So it's going to be 7 choose 3, or 7 choose 4, it doesn't matter, with 3 of those, so that cubed, and 4 of those, and just type all the numbers into a calculator, and you end up with this. And so that's the coefficient of t to the 6, which is the coefficient of t to the 6 to the 15 in the original thing with the t to the 9 here. And so we get the probability of that there. Question number 7 then, a machine fills bag with flour. We've got a mean mu and standard deviation 30. Going to check if there's any change to the mean. So take a sample of 10, and the mean of that sample is 1020, and we're going to test at 5% whether or not the mean is likely to be 1000 or not. And it's going to be a two-tailed test, as we can see from here. So what we're going to do is we're going to set up the mean, or the x bar is normally distributed with 1000, because we're going to start with the null hypothesis as our starting point, of course. And then this here, well, the standard deviation is 30 over root 10, because you've got a sample here. But of course, when you square that, you get 30 squared over root 10 squared is just 10. And that's how I prefer to write it. We're going to standardize this. So we're going to take x, which is our critical value, minus 1000 over this standard deviation here. And now it's two-tailed, of course. So we need to find the value that gets to this end. And of course, to do that, we can just, in a calculator, do inverse normal area 0.025, because half of 5% is 2.5%. We're going to look all the way down here to start with. And that gives us a value of this. You can just quote minus 1.96. You're allowed to do that. That's fine. Of course, when we solve this, multiply this over here, add 1000, we get it as this. And then for the other end, of course, inverse normal area 0.975. We, of course, just get 1.96 positively. Here again, you multiply this out 1000 and you end up with this. So this is kind of like our confidence interval. And we've got a mean of 1020, which is outside of this interval, and therefore we will reject H0. And there's evidence that there's been change to the mean of each, change in the mean of each bag. Good. Now he decides to alter the test so that it's just one-tailed, but keep this level of significance of 5%. He's also going to take a sample of size n, which is going to make this slightly more complicated. So what we're going to do is the same thing we sort of did before, but change the 10 for an n. So that's just the same idea there. And then we can standardize this again to look for our critical value, which I'll just call C, because that's kind of what they've called it. But now I need to do 30 over root 10 on the bottom here. I'll do the same thing. So it's 5% this time, but it's one-tailed. And it's at the top, right, at the top of the distribution, because we're being bigger than this. So inverse normal 0.95 gets us to this value. If you multiply this over there, another 1000, you'll end up with this here. So, okay, so that's the equation for C in terms of n. The last 5 marks of the paper then, the true value of mu is 1020. And it starts talking about type 2 errors. This is very similar to what the 2021 paper did as well. Now, what we need to do here is we need to get out a double normal distribution graph. And this is going to make things much clearer for us. Now, this black graph represents the old distribution, the H0 distribution we were working with earlier, with mean of 1000. And we've worked out this C value here, whereby the area above it is 5%. So let's pretend this area down here below the black graph is 5%. And that critical value C is this, according to whatever n, the size of the sample is. So that's where we're at so far. Except now we're told that the true value of mu is 1020. So we're not actually in this distribution here. We're in this distribution with mean of 1020. And a type 2 error is when you accept H0, but H0 is false. Now, we did this before, right? The way that we accept H0 is if we're below this critical value C, right? This critical value C says if you're below it, you accept this distribution here, and if you're above it, you don't. So therefore, to accept H0, we need to be below this value of C. We need to be in here. But of course, H0 is actually false. This is the true distribution. So therefore, below C to accept H0, but this is the true distribution, is in this area here below the red graph here, just this area here. And we want the probability of that. We want the area of this region below the red graph right here. We want that to be 0.005. So what we do is we get out a standardized thing again, and we say C minus 1020 this time, because we know we're living in this distribution over that same value we had before, is equal to, and then inverse normal area with 0.05, because we're at this left-hand end of this red curve. So this here, for this value here, is going to give me this value here. Of course, we can, at this point, it's actually just algebra from this point. We can replace this C with all of this stuff to get this. So just replacing that C with all this, I can now just multiply across here. This is just what I wrote down. Multiply this stuff across here, you get this. Add this to both sides, add 20 to both sides, you end up with this. Times by root n, divide by 20, and you get n is this. Square both sides, you get this. And now this has been, a type 2 error is rounded to this thing, to two significant figures. So I'm assuming the true value of this is just 40, and that's what causes the rounding here. So we'll just say n is 40. And of course, we can pop that n is 40 into here to find our C value, and we get C as this. And that's the entire paper. Thank you for watching, and I'll see you next time.